your last statement. You said the test is on unit 6.
No, the test will end at 6. That is
That,
the last part the test will go up to.
oh, okay.
So
Good.
yeah, nothing beyond unit 6 will be in the test.
Right. Thanks.
Okay. All right. Then let us get started. So today we will start with Unit 5. It's not a difficult topic, and you have done most of these questions in your assignment before, so I'm sure none of this will be difficult. So what we will be doing is inferences about the variance. This is chapter 5 or unit 5. About So far what we have done has been on the mean and the proportion. We've worked out confidence intervals for, just excuse me. Okay, I'm back. So as I was saying, we have already done inferences about the population mean and the population proportion. Okay, guys, bear with me. It's Monday, so you know how that goes. Okay, but hopefully we will get through this today. What we are going to basically do is the same thing we did with the population mean and the proportion. The first thing was the confidence interval, where you can say you're 95% or you're 99% confident that the variance or the true population variance is in that given interval. And then after that, we look at inferences that are made. So somebody makes a claim like the variance in this population is this much, and then you will do your hypothesis testing. So you'll have a null hypothesis, an alternative, you get a tested statistic, and so on. So everything else will be the same pretty much, except this time we're not dealing with mean and proportion, but with the variance or standard deviation. Because if you have the variance to get the standard deviation, all you need to do is take the square root. Okay, so what I want us to do today is we are just going to look at some examples. I think it's best you work with an example, and then everything else you do it in pretty much the same way. Now we start with a confidence interval. Now, if you want to work out a confidence interval of your population, what you need to do is you use this formula, just like with the mean and the proportion. We had a formula that we used to calculate the confidence interval. Here we do the same thing, and our formula is like this. We have n minus 1 s squared over, this is chi squared alpha over 2 n minus 1. This is less than your sigma squared, which is less than n minus 1 squared over I squared 1 minus alpha over 2 and then n minus 1. That is your degrees of freedom. Okay, so with the mean and the proportion, we used Z or the T. Now here what we do is instead of Z, we use what is called the chi-square. So the chi-square is another distribution that we make use of. The only difference is in the way that it looks, but everything else we do with the chi-square will be pretty much the same as what we did with the Z and the T, and we already know how to work with the degrees of freedom. Okay, so the chi-square looks something like this. So something like this, and this is not symmetric. Okay, so unlike the T and the Z, they were symmetric, but this one is not. But the reading, everything else, we will do it in pretty much the same way. So if I tell you I want a 99% confidence interval, your alpha is 1%, which is 0.01. So you will substitute that here, read or calculate your degrees of freedom based on your sample, and then substitute, and then these values over here, you will read them from the table, but we'll look at how to do that. Okay, so that is the formula. Now let's look at an example. Okay, in 16 test runs, petrol consumption of an experimental engine had a standard deviation of 2.2 liters. Then we have to construct (99% confidence interval for the variance sigma squared. So make sure you do the correct one. Sometimes they will say the standard deviation, so you construct a confidence interval for the standard deviation. At other times it'll be a confidence interval for the variance. So if you're asked to work out the confidence interval for the standard deviation, all you will do is you'll take the square root on both sides over here. Okay, then sigma squared, then we are measuring the true variability of the petrol consumption. Of this engine. Okay, Right. So with questions like this, we assume that the sample is normally distributed. But again, the reason we're not using a Z or a T is because we're not dealing with the mean or the proportion. Those go with the mean and the proportion. But with variance, we deal with a chi-square. Okay, so we can write down what it is we are given. So we're told that we have 16 tests. So that means n is equal to 16. Let me just write solution here. Okay, so we know that n is equal to 16. Then the standard deviation from the sample is 2.2. So S is equal to 2.2. Okay, so if we look at our formula over here, the only thing we don't have is this one over here, which we need to get from our table. This S squared, we can always work it out because we know that S is 2.2. So to get S squared, we just square our 2.2. So this one over here, we need to read it from the table. So we look at the chi-square, and here our alpha. So we want a 99% confidence interval. So that means our alpha is 1%, because you always say, what do I need in order to make this 100%? I need 1%, and 1% is just 0.01. Then I'm looking at this formula over here. I need to divide my alpha by 2. So this 0.01, I will divide it by 2. When I do that, I will get 0.005. So it'll be 0.005. And then my degrees of freedom is just 1 less than n. This is 15. Okay, so I'll write that down, and then we'll look at the table. Then we have the chi-square of this one over here. It's 1 minus alpha over 2. So what I need to do is subtract that 0.05 from 1, and then that will give me my value over here, and then the degrees of freedom are the same. So here, what I will say is 1 minus alpha over 2. This is equal to 1 minus 0.05 divided by 2. This is equal to 1. This is 1 minus 0.005, and this gives us 0.995. Okay, so here I have 0.995, and then the degrees of freedom are still 15. So this is just the working of how we do it, but again, very basic arithmetic, nothing too complicated there. So what we do now is we go to our chi-square table. So I'm going to try, let me see if I can get the chi-square table and show you guys how we do that. Okay, not this one. Okay, just do it like that. Okay. Right. I hope you can see my chi-square over here. So that is what it looks like. So again, it is not symmetric, but the way that we read off of the table is pretty much the same. It's pretty much the same as we have been doing so far. So we have, let me see, we have here 0.005, 15. So we will look for this value and then that number of degrees of freedom. So let's go to our table. There it is. So looking for 0.005. There it is in the last column. Okay, then we said we want 15 degrees of freedom. So 15 degrees of freedom over here. So this is the value that we're looking for, 32.80132. So the 0.05 or your alpha over 2 or 1 minus alpha is in the first row. Your degrees of freedom are in the first column, and then you see where the two match depending on what you're looking for. So 15 degrees of freedom and 0.05. So if we write that down, this is 32.80132. Okay, then we do the same thing for this value over here, 0.995, 15. So we go to our chi-square. So 0.995 is over here. The degrees of freedom are 15. So this is the value that we're looking for. Then we write that down. This is 4.60092. Okay, so now that we have that, all we will do now is substitute the values and then get our confidence interval. So this is the formula again. We have everything n minus 1. That's 15s squared, the 2.2 squared. And then these values over here, we read them from our table, which we did just now. So doing that, our confidence interval will then be we said 15 multiplied by 2.2, which I square. Then I divide by 32.80132. This is less than sigma squared, which is less than 15 times 2.2 squared, and this is divided by 4.60092. And this you just do on your calculator. I like to leave it to 4 decimal places. I think that's a good approximation. So I'll write down the whole thing I got from the calculator and then round off to 4 decimal places. So here, when you work this out, 15 times 2.2 squared over your chi-square value, you get 2.2133255561. And over here, 15.80132. 7, 7, 9, 4, 5, 2, 8, and 1. Okay, then is sorry, before that we rounded off, so I say 2.2133, and then this is 15.7795. Okay, and then after that you write a statement as usual. We are 95 or 99% confident that the true variance lies in the interval from this to that. So you can phrase it a little bit differently as long as you state those key things. You're 99% confident, the true variance, and these are the values that it lies between. You can say we are 99% confident that the true variance just see Okay, so that is how you would answer it. So again, you can see nothing too complicated here. As long as you remember the formula, then read your values correctly from the table. So make sure your alpha is correct and the degrees of freedom are correct. Then I like to leave it to 4 decimal places and then write a statement answering the question. So in your statement, again, I want to see how confident are you. This is a confidence interval for what? So you can say the true variance, and then you tell me what the confidence interval is. Okay, are we fine with that? Okay, and let's look at another example. This is example 2. So with this one, we will not be given the sample standard deviation. What we will have to do is work it out, but we know how to do that. We know the formula to do that. So with a small sample, even if the standard deviation is not given, it's not a difficult thing to work out. So we're told that the following are weights in grams of 10 packages of grass seed. That is seed distributed by a certain company. So the values are 46.4, 46.1, 45.8, 47.0, 46.1, 45.9, 45.8, 46.9, 45.2, and 46. So 46.4, 46.1, 45.8, 47, 46.1, 45.9, 45.8, 46.9, 45.2, and 46 or 46.0. Now what we need to do is find a 95% confidence interval . Confidence interval for the variance of all such packages of grass seed. By this company. And here, assuming a normal population. So again, even if the population is normally distributed, for variance and standard deviation, when we make inferences about them, we will use the chi-square. So don't be thrown off by this. It's a normal population, so that means you must use the Z or the T. No, with variance, we use a chi-square. Okay, so this is the question. What I want you guys to do is we'll take about 2-3 minutes. You guys work it out and then we will go over it together. So you can see from this question, we're told what n is. We know n is 10. We don't have s, it's not given to us, so we will have to work it out. These are 10 values, not very difficult to get, so you should be able to do that. And then the only thing you need are the chi-square values from your table. So can you take about 2 or 3 minutes, work it out, and then we will go over it together. Okay, so I hope you have solved it by now. So it's not a difficult one to do. So like I said, the very first thing we need to do is work out what our s squared is. And we know what our formula is for working that out. We know that s, or s squared, this is equal to the sum of the squares minus the sum squared over n. Then this is all divided by n minus 1. Okay, then we will work out what each of these values is. So the sum of your x squared here, can somebody tell me what did you get for this over
21,093.92. 21093.92.
I said that's not what I got. Anybody else get 21,000? I got 21,000 and something, but not what you are saying. Did anybody else get something different? Okay, what I got, 21,273.12. Did anybody else get this? Monday is always so quiet. Nobody's saying anything. Did anybody else get what I got?
No, well, I don't know about the others, but it's the same, the basic principle, taking every yeah, never
Every
mind.
entry and squaring it.
Yes, sir. Yes, every entry, and then we square it. So I did all of that.
Okay.
46.4.
Okay, and then for this one, the sum you squared, so you add each of the individual entries. Then what I got is a 461.2, which I will have to square, and then this you divide by 10, and then finally divide by 10 minus 1, which is equal to 9. Okay, so this is all the entries squared. This is the sum of all the entries that I will need to square and divide by 10 because there are 10 entries. And then this is 10 minus 1. Then this I just type in on my calculator. And what I got is 0.286. Then 222, and then it continues in that manner. So to 4 decimal places, this is approximately 0.2862. Okay, so now we know what our s squared is. We're almost there. So just to go back to the formula. So we need n minus 1, which we have. We needed s squared, which we just got. Now we have to read this value from our table. So chi squared, and we said alpha divided by 2. Now here our alpha is 10%. Did I say 10? I think the question here, maybe I didn't copy it right. No, it is 95. Okay, no, that's fine. Okay, so it is a 95% confidence interval. So alpha is equal to 0.05. Then we will divide that by 2. And we get 0.025. And then our degrees of freedom are just 10 minus 1, which is equal to 9. So this value we'll read from the table. And then we have the chi-squared of 1 minus alpha. So this is 1 minus 0.025. This is 0.975. And then the degrees of freedom is also 9. Okay, so this is what we need to read from a table. Let me see if I can get the table now. Okay, so here is my table. Let me see. Let me try and turn this. Okay, I hope you can see my table. So we said that the first one, we have chi-square alpha over 2 is 0.025. So we look for 0.025. There it is. And the degrees of freedom are 9. We have 9 degrees of freedom. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 19.0227. So this one over here. Okay, I can't highlight it over there. Okay. This is 19.0227. And then we do the same thing for this one, 0.975 and 9 degrees of freedom. There is our table. 0.975 and then 9 degrees of freedom. There it is. This is 2.70039. Okay, then we have everything we need in order to construct the confidence interval. So we do that. So our 95% confidence interval will be this n minus 1. This is 9. Then we multiply this by s squared. This is 0.2862. So I'm using the 1 to 4 decimal places. And then I divide by chi-squared at alpha over 2, comma n minus 1. This is 19.0227 squared. And again, this is 0.2862. Then we divide this by 2.70039, and that's it. So these two values over here, you just work them out on your calculator, and I hope we got the same thing. This is 0.1354. And I got 0.9537. Then again, you write a statement and say we are 95% confident that the true variance for the grass seed packages lies in the interval from 0.1354 to 0.9537. That's it. So again, it doesn't have to be exactly the way I've said it, but there are key things that I'm looking for. So the confidence level, what the interval itself is, that it is the true variance, and then include some of the words from the question. Okay, so that's it on confidence interval. So it's pretty much the same as what we did with the confidence interval for the mean and the proportion. All you had to do was use that formula. You know the formula, you just find the individual parts of it that you need, substitute them, and then you have your answer. Then the next thing is hypothesis testing for single population variance. Okay, so just like hypothesis testing for the mean and the proportion, we had 5 steps that you had to follow. The first thing you do is you state your hypotheses. You calculate your Z statistic here. It will not be your Z or your T here. It'll be your chi-square calculated variable. Then you have a decision rule to state. You make a decision and then you write a conclusion. So we're going to follow pretty much the same procedure over here. Now the only difference is here our null hypothesis is always going to be the one that stays equal to. So our H naught is always sigma squared is equal to some hypothesized value. Okay, so this can also be standard deviation, but you will always have an equal to over here. So unlike with the mean and the proportion, your null hypothesis could be less than, it could be greater than, but with us, we will only stick to this one where it is equal to. But our alternative hypothesis can be one-tailed or it can be two-tailed. So H naught, HA can be either. So you'll have HA like this. Sigma squared is less than the hypothesized value. HA is not equal to the hypothesized value, or HA sigma squared is greater than the hypothesized value. Okay, now the first one and the third one, these are one-tailed tests. So this is one-tailed. This is also one-tailed. This is upper, and this one is lower tail test. Okay. Okay, so that is a lower. And then the one in the middle over here, this is a two-tailed test. So with a one-tailed test, so let me see, this is number one. Number one, the lower. Over here, this will be your rejection region, that one over there. And this value over here, your critical value, will be chi squared. This is 1 minus alpha. And then you have your degrees of freedom. So this one in black over here, that is your rejection region for a lower tailed test. Then the upper tail test is just the opposite. You'll have it maybe somewhere here. But then the second one, you have like that. So you have two rejection regions like that. And this is chi squared, 1 minus alpha over 2. Then you have your degrees of freedom, n minus 1. And then over here, you have chi squared alpha over 2, and then n minus 1 degrees of freedom. And then the last one is an upper tail test, so you will only use that one over there. But everything else is going to be pretty much the same. So you have those 5 steps. You say, okay, step 1, this is what I need to do. You do it, move on to the second one. Eventually, you will always get to the right answer. So let us look at an example of this. You're told that a manufacturer of car batteries claims that the life of his batteries is approximately normal. Is approximately normally distributed. If a random sample of 10 of these batteries has a standard deviation of 1.2 years, do you think that 0.9 years use a 0.05 level of significance? Okay, that's level of significance. Okay, a manufacturer of car batteries claims that the life of his batteries is approximately normally distributed. if a random sample of 10 of these batteries has a standard deviation of 2 years, do you think that sigma greater than 0.9 years is true, or do you think that sigma is greater than 0.9 years? Then we have to use a 0.5 level of significance. So like I said, we will follow pretty much the same steps that we did when we're doing hypothesis testing for the mean and the proportion. So first thing we need to do, step 1, is our hypotheses. Okay, so we say that H naught is always that sigma is equal to whatever is claimed. So here the hypothesized value is 0.9. So my null hypothesis is just that sigma is equal to 0.9. Okay, and notice here we're working with sigma and not sigma squared. Then our alternative is whatever. So here we're asked to check that if sigma is greater than. So here we have an upper-tailed test. So this is going to be our alternative hypothesis. So we have sigma is greater than 0.9. So the equal to in the null hypothesis, that is what we will always be testing when it comes to the variance. With the mean and the proportion, you can have less than or equal to, greater than or equal to, but with our variance, we will always have an equal to over there. Okay, that is step number 1. Then step number 2, we need to calculate the test statistic. So step 2, we need to calculate the test statistic. So here our chi-squared calculated will be n minus 1 multiplied by s squared over sigma naught 2. Now this sigma naught over here, that is just whatever your hypothesized variance or standard deviation is. So this, whatever you have over here, that is what you are going to substitute over there. Okay, so we work this one out and get our test statistic. We substitute the values. So this is a sample of 10. So I will say 10 minus 1, which is 9. Then our s squared, we are told that the standard deviation is 1.9. So s squared is just 1.2. So the sample variance, or s squared, is 1.2 squared. So I'll multiply this by 1.2 squared, and then we divide by a hypothesized variance, which is this one here. That goes with the null hypothesis, but we will have to square it. So this is 0.9 squared. So this you do on your calculator. When I did it, I got 16. Okay, so that is step number 2. Then step number 3, we need a decision rule. This is our decision rule. So we say that this is an upper-tailed test. So our critical value is somewhere over there. This will be our rejection region. So this is our rejection region, and the rejection region has an area of 0.05. So what we're looking for is this value here, and this is just chi-squared 0.05, and then the degrees of freedom is just 1 less than n. So here our degrees of freedom is 9. Okay, then this we read from our table. So I'll just pull up my table now. But I'm sure you guys are quite familiar with reading from the table by now. Okay, so we say that our alpha is 0.05. That is over here. The degrees of freedom is 9. So here we have a 16.91898. Okay, so that is our critical value. So this is equal to what we got from the table. We said 16.91898. Okay, then now we state our decision rule. So the rule is we will reject H naught if the chi-squared that we calculated is greater than 16.918. Okay, so that is our decision rule. Then step number 3, we need to actually make that decision. Sorry, step number 4. Step 4, this is what our decision is. So if we look at what we got over here, this is our calculated value. We say that we will reject H naught if the calculated value is greater than our critical value over here. Here we have 16, over here we have 16.9. This is obviously less than that, so we will fail to reject H naught. Okay, we say that since chi-squared that we calculated is equal to 16, which is less than 16.9898, we fail to reject H naught. Okay, so if we fail to reject H naught, then we have to state what that means in terms of the battery. Okay, then step 5. This is our conclusion. We conclude at 5% level. Okay. Level of sigma. That there is not enough evidence to conclude that sigma is greater than 0.9. Okay, so we'll go back to the question. Okay, that is what we're asked, whether sigma is greater than 0.9, and then our answer should be in line with that. Okay, so you can see the 5 steps that I used, hypothesis testing for the mean and the proportion. These are the exact same 5 steps that I'm using over here. Now let us look at a lower tailed test.
Ma'am?
Yes.
Okay, so I'm kind of confused, or I'm not getting it really. On step, when do we know when we should fail to reject and to reject? Like
Okay.
that
Yeah.
thing confusing right now.
Are you still there?
No, I'm still here.
Okay. I didn't get your question. You said, when do we fail to reject, or what's the question? Can you say it again?
How do you know, like, the statement to write? Like, how do you know when to write we fail to reject H, and or we reject the, the hypothesis?
You look at your decision rule. So remember, we had a decision rule over here. Do you understand how we got the decision rule over here? I'm
Yes,
not sure.
how
Okay,
you
I'm
got
not sure. Is it on the wording when you say you fail to reject, or and when you say you reject? Are you talking about the wording of it?
it.
Okay, the wording, this it's just a statistical term. Just like in a court, you don't say you're now found guilty, you're now found innocent. The court, you never find somebody they're proven innocent. The person is found not guilty. That's the verdict. Okay, so here also it's a statistical term. Either you reject or you fail to reject. So if you can think of it as you're accepting, but we don't use the word accepting. We just say we fail to reject. I hope that answers your.
Yes.
Okay. So it's like a statistical term that we use. So instead of I'm accepting the null hypothesis, we don't say that. We say you fail to reject it, or you don't have enough evidence to say it is not true. That's basically what we're saying. So most of the time you don't want to just say, yes, it's definitely true. You say, no, we don't have enough evidence to show that it is not true. That's what it means to fail to reject it.
Oh, okay. Thank you. That.
Okay. All right. Then let's look at a lower tailed example. This one. Okay.
Hello, ma'am.
This is a lower tail test.
Hello.
Yes. Go ahead. You have a
Yes.
question?
Yeah, yes, ma'am. I just wanted to ask: is it possible to end the class earlier for us also to have time to join the other class? Seeing that there's only 10 minutes left now.
Okay, I think we'll be able to finish just one example now, because we need to finish this. Wednesday is a public holiday, so
Yeah.
we won't have class on that day, and we still have to do unit 6 to cover that before the test. So let me at least finish this one example. If I go a little bit beyond than just leave. I'm recording this, then the part that you missed, you can just watch it later on. Okay, but today we really need to finish this one. Okay, so we say that this is a lower tailed test example. We have a company that claims that the standard deviation of the length of time it takes an incoming call to be transferred to the correct office is less than 1.4 minutes. Now we have a random sample of 25 incoming calls, has a standard deviation of 1.1 minutes. Then we say at alpha equal to 0.1, is there enough evidence to support the company's claim? Okay, then we assume the population is normally distributed. Okay, so a company claims that the standard deviation of the length of time it takes an incoming call to be transferred to the correct office is less than 1.4 minutes. A random sample of 25 incoming calls has a standard deviation of 1.1 minutes. Then at alpha equal to 0.1, is there enough evidence to support the company's claim? We assume that the population is normally distributed. So to test this hypothesis, all we do is we go through the 5 steps. So for this one, I'm not going to write step 1, step 2, step 3, and so on. I'm sure you know what each of the steps is already. So the first thing we said is we need our hypotheses. So we say that H naught, this is that sigma, because we're talking about the standard deviation, this is equal to 1.4. So again, with the standard deviation, we always have an equal to over here. And then our alternative, this is the claim or whatever it is you're asked in the question. So the company claims that the standard deviation is less than 1.4. So this is the claim that is stated in the question, or the claim that the company says. Then step number 2, we need to have our test statistic. So we say that chi-squared that we calculate, this is equal to n minus 1 s squared over the hypothesized value squared. So this is equal to n minus 1. We took a sample of 25 calls. So it's 25. So we'll say 25 minus 1. This is 24. Then the standard deviation from our sample is here. It's 1.1. Then we will square that. 1.1 squared. And then we divide by the hypothesized value. This value is whatever you have in your null hypothesis. So this is 1.4 squared. And that you just work it out on your calculator. I got 14.81632653. Then to 4 decimal places, this is approximately 14.8163. Okay, then step number 3, we need our decision rule. So if I draw the chi-square distribution, something like that, we say that this is a lower tail test. So we'll have this value, and this is going to be our rejection region. Now our critical value over here, this will be chi-squared, and then I have 1 minus alpha. And here I have n minus 1. So with the lower tail, it's not alpha over here, it's 1 minus alpha. And then the degrees of freedom is still n minus 1. So this is just chi-squared. Then 1 minus alpha. Alpha, we are told in the question, is 0.1. So 1 minus alpha is 0.9. And the degrees of freedom, this is 24. And this, when you read it from your table, you should get 15.65868. Then you state what your decision rule is. You say, I will reject H naught if a chi-square that I calculate is less than, because that means it will fall in this rejection region. If it is less than 15.65868. Then the next step is to make your decision. So you'll look at this value that you calculated, then compare it with your critical value. So here it is definitely less than our critical value. So that means we will reject H naught. So that's step number 4, our decision. Since the chi-square that we calculated is less than the critical value of 15.65868, we reject H naught. Then we say that at 10% level of significance, so this is the decision and the conclusion in one, a 10% level of significance, there is enough evidence to support the claim that the standard deviation for the lengths of time takes for an incoming call to be transferred is less than 1.4. Is less than 1.4 minutes. Okay, and that is it. So in the next class, which is probably just going to be a video that I record, because like I said, on Wednesday, it's a public holiday, so we will not have a live class on that day. I will record a video maybe today or Wednesday morning, and while you're in the line, you can watch it and study, or yeah, get ready for the test. And that will cover unit 6, which is going to be part of the test. So the test, when I last checked in the course outline, it is on Monday the 30th. It is an online test. I think only the comprehensive test is the one that you are supposed to write face to face. So this test should be an online one. Okay, so we'll stop here for today. Have a good evening, and I will see you guys Monday probably. But if you have questions, please do contact me. Call me on Teams or come to my office